Well, hello everyone and welcome back to Adrian's Digital Basement. On today's video, I have several MFM hard drives here on the bench, including the Seagate ST-225. I don't know if any of these drives work, and I'm going to try to get them working in this video. And along the way, I'm going to talk a little bit about, well, how these drives work and some of the options you can use for controlling them and software that you can use to try to diagnose them. So without further ado, let's get right to it. So the humble MFM hard drive. Actually, the term MFM hard drive is actually just a colloquialism, and the technical name for these types of hard drives are ST-506, based on the very first model of this type of hard drive that had the interface that all of these drives share. If you have any experience at all with an MFM type hard drive, it probably comes from its use inside of an IBM PC or PC compatible machine. The thing is, the very first IBM PC, the 5150, did not come with a hard drive from IBM. It wasn't until the IBM PC 5160, the XT, that they offered a hard drive option, but the very first Seagate hard drive with this MFM standard was released in 1981 before the PC was even sporting a hard drive. So these MFM drives were not designed for use with a DOS PC, but it seems like that was the most common use. And because that ST-506, which I don't have a specimen to show you, was not designed for the PC, you can actually find these types of hard drives with this type of interface in all sorts of machines. I actually have a Mac 512 that has a hard drive added to it, and it's a 3.5-inch MFM hard drive. Could be similar to this one, to be honest. I don't remember exactly which one is in the Mac I have, but it has the exact same MFM style interface as this drive right here. Before we take a closer look at the hard drives I want to try to get working today, let's do a little bit of reading about the history of this particular type of hard drive. So as I mentioned, these were early hard drive products. It actually says that the ST-506 came out in 1980, which I'm not sure that's totally correct. I say that because the ST-506 preliminary manual has a date of April 1st, 1981, so not quite sure what the real date is. Either way, the article goes on to say that it was the selection of this type of hard drive system for use with the IBM XT which made it the de facto standard in the computer industry. The article calls it the ST-412 interface in addition to the ST-506 interface because it was the actual ST-412 that was selected by IBM for use in the original PC XT. A quick search for that model number shows that this was a full-height 5.25-inch disk drive, and I've worked on a couple IBM XTs that had this exact hard drive in it. But it was actually the ST-506 which originated the disk interface standard used across all MFM hard drives that then was used on the ST-412. Now, one thing a lot of retro computer enthusiasts may not realize about this ST-506 or MFM hard drive interface is that it's heavily based on the floppy drive interface. If you've ever worked with MFM hard drives, you may have wondered why the drive interface cables have at least one of the cables being a 34-pin cable that's basically the same as the floppy drive cable. The ST-506 interface between the controller and the drive was derived from the Shugart Associates SA1000 interface, which was Shugart's very first consumer hard drive, an 8-inch model. And the SA1000's interface was in turn based on the floppy drive interface, and it is that SA1000 that used a 50-pin ribbon cable to connect the drive to the interface controller, which had almost the same pinout as the 50-pin ribbon cable used for Shugart's own 8-inch floppy drive. Now, the 8-inch floppy drive was not invented by Shugart, it was invented by IBM, but the Shugart SA800, which was their 8-inch floppy drive, was widely used across all other systems besides IBM, of course, and it was Shugart who came out with the SA400, which was their 5.25-inch floppy drive, which is what introduced us to the 34-pin disk interface connector that we are still using today if you're hooking up a floppy drive to a computer. Seagate took that 34-pin floppy drive interface from the SA400 floppy drive that Shugart came up with, and they adapted it to support hard drive duties. Now back to the article, it does say here the limitations of that ST-412 or 506 interface is that it runs at 5 million transitions per second, which is basically 5 megabits per second. It supports up to 16 heads, 4 drive units, and up to a 20-foot cable length. I don't think I ever saw an MFM hard drive hooked up outside of a computer with a 20-foot cable. You always had these types of ribbon cables on the inside, but theoretically it was possible. Now, as I mentioned earlier, the colloquial name of this type of hard drive is MFM hard drive, or the MFM interface, and that's simply because it uses MFM encoding to save, read and write data from the disk. This is exactly the same type of encoding used on double density diskettes, as I had mentioned in my recent disk drive video. Now, I'm not sure who originated this, but a later version of the interface came out. It was the RLL variant, which used exactly the same signaling, but instead of MFM encoding, it was using RLL, or Run Length Limited encoding, which has the benefit of increasing the amount of storage space by 1.5 times, and the data rate went from 5 megabits to 7.5 megabits. So you got better performance, and you got higher data density on the disk. Now, I had been planning to make a video on this, and maybe I still will, but that means that a hard drive like this that might store 40 megabytes with MFM encoding, when used with an RLL controller, which simply increases the density that's written to the disk, means that it can store 60 megabytes on the drive. Now, the thing is, RLL is more susceptible to variations in RPM and speed of the disk, so you could have data errors if the mechanism wasn't up to snuff. People always said you should use the specific RLL versions of the hard drive when using an RLL controller, or you could have problems. But I've done some testing, and actually it seemed like everything I ever used worked. This is very similar to the way that floppy disks can be written with both FM, or frequency modulation encoding, or modified frequency modulation encoding, MFM, and generally that's the difference between single density and double density. It's the same media, the same disk drive, but different encoding method, which increases the possible data storage capacity on the drive. I've never personally heard of media or a floppy drive that could only record at FM and would not work at MFM or double density with the appropriate upgraded controller. And that kind of begs the question, what if you took a floppy disk and you used RLL encoding on that? Could you increase the capacity again 1.5 times what you're getting with MFM? It's possible. I've never heard of that done, but that certainly would be a very interesting experiment to try. Back to the article, it's talking about the connections you make from the interface card to the disk. And remember, it's using these two edge connectors, and you are using two cables, a 34-pin cable and I think a 20-pin cable. Now, the reason for this extra cable that you don't have on a floppy drive is because that increased data rate of 5 megabits per second over a floppy drive's 250 kilobits per second or 500 kilobits per second necessitated the use of differential signaling, which you can see right here on this 20-pin connector. We have a differential write signal and we have a differential read signal. It's really the only thing that comes across this line in addition to this drive selected on pin 1. If we compare the 34-pin connection between the hard drive controller, which is on the left, and the floppy drive, which is on the right, there are some differences where the signals are all swapped around, but a lot of the signals are very similar in the way they work. Take the direction signal, which is what tells the disk drive which way to move the heads when the step line is toggled. That's pin 20. That same direction pin is on the hard drive, as is the step signal, which is what actually moves the head one direction or the other. There's a line for track 0. That means when the head of either the disk drive or the hard drive is at the track 0, it actually asserts that line. And on the floppy drive, the head select, which allows you to select between head 0 and 1, is actually replaced by 4 head select signals, 0, 1, 2, and 3, which are actually binary coded decimal that allows up to 16 heads to be used instead of the single 0 or 1 on the floppy drive. Now, I've never tried this, but I have a feeling you could rewire the connector that goes to a floppy drive and actually get some very rudimentary head control on one of these types of hard drives from a floppy controller. Now, with the original XT, you ended up using an 8-bit floppy drive controller, sort of like this one, although this is an actual RLL controller, but it looks exactly the same as the MFM type. You'd pair that with your hard drive, which would be mounted inside the computer through those ribbon cables we just talked about. Now, the thing I want you to consider is that the electronics that are actually on the hard drive aren't doing very much of anything. All they're really there to do is spin up the drive itself when you apply power, and then have the right electronics to control the stepper assembly, which is this right here, to move the heads around, and to also amplify the signal that's being read off the disk and send that over to the controller, or vice versa, take the signals coming from the controller that are going into the drive for writing and actually write them onto the disk. That is all this is doing. There are really no intelligence at all inside of this hard drive. It's all contained in the controller chip that is on the hard drive controller inside your computer. And that's really one of the reasons why you can replace your controller, an MFM controller, with an RLL controller, and that will actually change the encoding because the disk controller in your computer is doing the encoding for the disk. It just sends it over the ribbon cable to the drive, which actually saves it through the read-write heads right onto the disk. You could really consider that these MFM hard drives are the equivalent of a dumb hard drive because there's really nothing that the hard drive can do on its own without the controller that it's attached to. Later, when hard drive capacity started increasing, like with this IBM H3133, I think it's 133 megabyte IDE hard drive, well, what IDE stands for is Integrated Drive Electronics. And when we flip this over here, you can see it's a highly integrated controller here on the bottom of the drive. They actually took what was on the controller card itself and what was on the hard drive here, and they combined it into one board. When you're using an IDE hard drive, you used a controller like this plugged into your system, and you had a 40-pin ribbon cable that went from this controller card to the hard drive. But the reality is, this card right here is not actually a disk controller at all. Most, or pretty much all of the electronics you see on this are actually to support the floppy drive and the serial ports and the gain port and whatever that's on here. The IDE port itself, this 40-pin connection, is actually just an extension of the ISA bus over a ribbon cable. Literally, these lines that come off the 16-bit slot here, these upper data bits, they go through a resistor right to this connector. There is no electronics at all in between. A little bit of electronics is required on this card for drive select, and also the mapping of the I/O port is handled on the card. But the reality is, everything for this hard drive right here to talk to the CPU over the data bus is on this card. It is literally a 16-bit ISA bus over a 40-pin ribbon cable. Now you might be noticing that this hard drive combo here has a controller that has a BIOS chip on it. And that's because this is an 8-bit controller card. And the original IBM PC and the PC XT had a BIOS on it, the IBM BIOS, that did not support hard drives natively out of the box. The BIOS did not know how to talk to a hard drive controller whatsoever. There was no standard for where it should be located in the I/O map or what commands were even used to talk to the hard drive controller. And keep in mind, the hard drive controller is this white IC on this card, and this is what the computer is actually talking to, which then interfaces to the mechanical mechanism of the drive over the ribbon cables. The ROM that's on this card is actually loaded at power on, and then that adds extensions into the regular system BIOS that allows it to then talk to the hard drive. That does bring some interesting limitations though. You may be familiar with the fact that hard drives like this have a different number of heads and cylinders and sectors per track. Well, that stuff is something you normally need to type into somewhere for the hard drive to work. The thing is, when you have a ROM BIOS on a card like this, that is actually hard-coded into the ROM chip. The controller card may only support a couple different types of hard drives that you would select with a jumper, or it may only select one type of hard drive. Now, there are some later 8-bit controller cards that have a little ROM routine you run with a little menu that pops up, and you can type in a custom heads and cylinders. And I think it's saved not into a non-volatile RAM on the card, but onto the hard drive itself. And then when you power on the system, it just reads that very first sector off the hard drive, which tells it what kind of hard drive it is, and then it configures itself from there. Here is a later 16-bit hard drive controller card. This is a Western Digital card, and when IBM released the PC AT, they actually worked with Western Digital to create their own card. It was an IBM type card, but it used Western Digital chips. It was really big, it had a lot of chips on it, but it had the exact same functions as this card. What IBM did is they moved the hard drive routines into the BIOS itself, and that's where those hard drive types have come from. So if you see type 1, type 2, type 3, all the way to type 47, that was from the original IBM PC AT. Because the ROM BIOS on the motherboard now supported talking directly to the hard drives, you did not need to have a ROM chip on the hard drive controller cards anymore. So 16-bit cards and onward don't need a ROM, and therefore you don't need to worry about using different types of hard drives that have a different number of heads and cylinders. When your 8-bit card might not support that because it might not be hard-coded into the ROM, it didn't matter later with the ATs, it added a lot more flexibility. So if you have a bunch of hard drives like I do that I need to be testing, you really need to use a 16-bit card like this, because that gives you the flexibility of setting the heads and cylinders in the computer's BIOS to match the actual hard drive you have connected. Now, when it comes to the commands that the IBM PC AT BIOS, the 5170 BIOS used to talk to the controller chip on this card, well, on the original IBM card, which then controlled the hard drive mechanism plugged in over the ribbon cables, those commands were pretty much set in stone when IBM released the 5170 and their MFM controller card. If you were going to release a non-IBM branded card like this Western Digital one, you had to use the exact same commands as that original IBM controller to maintain compatibility. And in fact, when integrated drive electronics drives first appeared, where they took this entire controller and shrunk it down and stuck it onto the hard drive, IDE drives also emulate that exact same command set that is on these hard drive controllers as well. Of course, IDE drives have some additional commands that may not be available on here, like figuring out the brand of the hard drive and stuff like that. That's the ATA part of the IDE. But for the basic reading and writing data to the drive, it works in exactly the same way. And that's why you can take a normal IDE drive like this 132 megabyte one, and using a more modern IDE controller like this, stick it into the original IBM PC AT with the original BIOS, and it will actually work. There are some timing considerations because the original BIOS wasn't expecting very fast hard drives, so it doesn't always work perfectly, but I actually have a patched BIOS on my 5170 video where we fix that problem with Stuart's help and allow the 5170 to use all fast hard drives, including compact flash cards, which incidentally, a compact flash card has an IDE emulation mode, which emulates this type of a hard drive interface, an ISA bus over the ribbon cable, which of course is emulating this type of controller card all the way back to what, 1983, when the IBM PC AT came out. Now, incidentally, one of the big reasons for going to IDE from this original ST506 interface was because the drive electronics were right on the hard drive, then you no longer had to worry about that ribbon cable with a 5 megabits transfer rate. You could go at a much faster transfer speed because the drive electronics are connected right to the read-write heads. Not to mention, you could use any encoding method you wanted. All of those commands that the computer is using to read and write data off the drive, those don't care about the encoding or any of that stuff. They just say, hey, write this data to this sector or read this data from this sector. So, because of the IDE drive's integration, we achieved much larger hard drives, but also much greater speeds. Okay, enough of that history and background. Let's take a look at these hard drives, which I want to try to get working right now. Alrighty, so here's the first hard drive. I'm starting with the one that's pretty much one of the most common hard drives that everyone has seen if you ever work with these old IBM PCs or any other old system that used MFM hard drives. The venerable Seagate ST-225. This hard drive, which came out in, I don't even know what year this came out in, is a half-height, 5¼ inch hard drive. There's a stepper motor that moves the head assembly, so this is not fast like the later voice coil types. This is pretty slow at moving the head around. Stepper motor was used on floppy drives as well. Of course, there's a lot more tracks on this thing, or called cylinders, but it still works and it's quite reliable, but it is pretty slow. Once you got around the time when drives were half-height, 3½ inch like this IBM drive, they were using voice coils to move the head assembly around. It's much more like an audio speaker where you have a permanent magnet or permanent magnets, an electromagnetic coil that is energized by the drive controller, and that allows very fast and precise positioning of the head assembly. That incidentally is still what's in use today with spinning hard drives. So hard drive technology hasn't changed a whole lot from this 132 megabyte hard drive you see here to what we're using today to store like 20 terabytes on a drive. Anyhow, back to the Seagate drive. Yeah, these were just incredibly common and they were used all over the place. This has a date here of 1989, second week, but I'm pretty sure that these drives were being sold into the middle of the 80s as well. So they're just very, very common. The ST-225, off the top of my head, I think it's 20 megabytes, but with all of these drives, I'm gonna have to go look up the heads and cylinders because unlike IDE drives, you can't just query for the size of the drive. You actually have to type that into the BIOS, or at least have to know that information and then type it into the BIOS. Typically, once I figure out if a drive works, I will then write the heads and cylinders and sectors per track right on the outside of the drive. So when it's time for me to go use it in another computer, I don't have to go look it up again. Alrighty, the next hard drive is this big boy right here. This is a Micropolis And let's see, you can just see right here, it's a full height 5¼ inch. It says May 27th, 1986 on it. I wouldn't be surprised if this is actually just a 20 megabyte hard drive, very similar to the Seagate ST-225 we just looked at. The original PC XT hard drive that IBM sold was a Seagate, 412, I think it said in the Wikipedia article, and that was also a full height hard drive, just like this one, except the one on the IBM only had 10 megabytes. And well, I'll have to look up what this is, but I don't even see necessarily a model number on here, but I'm pretty sure this is probably gonna be, whoops, a 20 megabyte drive, although I'm not totally positive. Incidentally, this wire here is just a ground wire that could connect to your case. I'm just gonna pull that off because we won't be using that. Now, it might be hard to see, but on the top label here, there is some printing, and these are the bad heads and cylinders on the disk. When the magnetic media is made, it's just not perfect. But what happens at the factory on more modern drives is they basically low-level format the drive and they do an analysis to find any of the bad sectors, and then those are mapped out in the firmware of the drive. They're just hidden from the operating system. So when you go use the drive, you try to write to a sector that's bad. Well, the drive doesn't even expose that bad sector to the operating system. So for what the operating system knows, the drive is totally good. Because these drives here are dumb, so to speak, and it's the controller that's doing all the smarts, there is no provision for any of that mapping stuff to go on, at least at a low level. So if the drive was certified from the factory, they would actually just print out all the bad sectors on this label here. And when you're going to low level your hard drive, which is lay down that base format onto the disk using software on the computer, you would type in all the bad sector information into the program and it would just skip over those bad sectors. So when the operating system itself was going to use the disk, just like with a modern drive, it wouldn't try to write to any of the bad sectors on the disk. Now I'm just reading what's on here and I see that it has from head 0 to head 6. There are bad sectors on head 6. That implies that this hard drive here is probably bigger than 20 megabytes. It most likely has 4 platters inside of here and a total of up to 8 heads. So that would be 0 through 7. But there are definitely a number of bad sectors on here. And when you low level a hard drive, you then run like a surface validation pass after that, just to make sure that all the proper bad sectors that are on there, at least from the factory, or new ones that it might have formed, are mapped out. If we flip this drive up to the front here, this has a full height faceplate, basically the same size as a full height floppy drive. And incidentally, this actually had a crack in it and I crazy glued it back together. And as usual with crazy glue, it does a pretty good job if you have a really clean break and you're able to put the glue and then squeeze it together with all those little imperfections. So I think this is doing pretty good. You can see the mark there, but it's better than the way it was where it was sort of hanging down. There is a drive access LED on the front, and this drive has the usual mounting mechanism with these screw holes on the side, which match up with what would be on a full height floppy drive. And on the back, it's just using the standard edge connectors for the interface. And there's also the standard Molex connector for the power. I have to put my goggles on here to see this, but the rated input power is 32 watts. Model number is 1325. So it's a Micropolis 1325, part number, serial number, you know, whatever. Okay, so this is the next MFM hard drive. This has a media flaw map that's just stuck on here with a piece of tape. What was originally put on the drive was this sticker underneath it, and it has no heads or cylinders marked on it. So someone manually wrote a heads and cylinder that was bad, probably later in use. In fact, I think this has a 1989 date code on it. And right here on the drive, it says 41st week of 1985. So this drive, I guess, is from 1985 or 86. And take a look at this sticker right here. It's a hard drive repair incorporated from Beaverton, Oregon. So this drive must have had some type of repair work done at some point. Maybe some piece of electronics failed or something, who knows? But it looks like it's been repaired at some point in its life. And on the end here, we have model number CM3426. Again, I don't see a brand anywhere on here, at least I haven't noticed it. But it's got the normal MFM type connections, although that doesn't look good right there. There's a kind of some bodged pin right there. I wonder if that was like one of the repairs they tried to do. That is really, really ugly. The only thing I see that looks sort of like a brand name, it says Donaldson on this little cap here. But that they could be the manufacturers of this little air filter cap. Who knows? Maybe there was a sticker like right here where this corrosion is that had the brand name and it fell off at some point. All right, here's the next hard drive. This is a 3.5-inch hard drive. It's MFM still. It's got a stepper motor right there. It is, well, I think I would say a full height 3.5-inch drive, because the half height, which is like this IDE drive here, is half the thickness of the normal, well, full height 3.5-inch, which happens to be the same height as a half height 5.25-inch drive. Yes, it's a little bit confusing, but I'm pretty sure, and people please correct me if I'm wrong in the comments below, that a full height 3.5-inch drive is the same height as a half height 5.25-inch drive. Either way, this thing is mounted in a mounting bracket here, so it fits in a half height 5.25-inch drive bay, which would be typical for a PC. It's going to be very hard to see because of this ridiculous sticker, but it is PTI, or Peripheral Technology Incorporated, in Simi Valley, California. Yes, there were a ton of hard drive manufacturers back in the day, and because of consolidation, all of them have disappeared, basically. They either got bought up by Seagate, Western Digital, or what, Connor. I don't know, there were a handful of ones that really lasted into the 90s, but in the early 80s and the mid 80s, there were a ton of manufacturers, companies that you will have never even heard of, who probably made a couple hard drives and then either went belly up or they got bought up by someone else. There's a sticker right here. It says it's made in Korea, so this might have been a Korean OEM making a hard drive for this PTI in the US. And I do have a sticker on here that I wrote 43 megabytes spins, but not responsive. And unfortunately, spinning but not responsive is a very typical condition of these old mechanical hard drives. You just can't really get them to do much, and we're probably going to encounter more of that with these hard drives. There's not a whole lot else to say about this other than it says PTI on the circuit board right here, and it's got surface mount components, passives at least, on here. And judging by the fact there's like not many through-hole things on here, this probably has surface mount ICs on the other side as well. A necessity when you were consolidating or shrinking the drive down to this 3.5-inch form factor. And this is the last drive we have here. It's a big boy. This is a Seagate. See if I can find a model number, but it is a full height drive. Let's fix the zoom there. Full height. It's very heavy. It's very big. There it is, ST-4051. I wouldn't be surprised if this is like a 50 megabyte hard drive, maybe unformatted capacity, 45 megabytes formatted. It has these things on it, which you might be wondering what these are. Older PCs, like the IBM PC 5170, the AT, it requires these drive rails to mount any type of device into its drive cage. These rails, which you screw onto the drive, allow you to slide the disk or the hard drive in and out of the machine, and then there are little caps that you screw on the front here, which kind of holds it in place so the drive doesn't fall out if you take the lid of the computer off. But they can be a problem if you have an old case and you don't have the drive rails. You can't put hard drives or disk drives in it. So hopefully you can find some, or you can print some on your printer. I ended up early on, back in 2016 when I got my 3D printer, one of the first things I did for it was I designed some drive rails for a particular case I had so that I could mount stuff in it, because otherwise the computer was pretty much useless if I couldn't put a hard drive or floppy drives in it. Anyways, looking at this thing, there's a good amount of corrosion on here, so that doesn't bode well for it. But there is a controller on the bottom of this drive here, and you know, there's lots of ICs there. And there's also a controller on the top of the drive in this area here. Now, I happen to know from these types of drives, I've used these before, that these use voice coils. So this is a more fancy type of head stepper assembly. And I think really that is because this large drive, I think, has 4 platters in it. So it has 8 heads and they weigh a lot. So using a stepper motor isn't really gonna work for such a big hard drive, hence the need for the voice coil assembly. So if I recall, the voice coil thing is here, and this moves the heads in and out on the discs like this. The discs are stacked up and the heads are imagined like this. They're like a fork and they go like this over the disc. Yeah, sorry, not trying to be phallic or anything. And wow, my fingers are getting really dirty. There are jumpers all over this thing. There are lots of tantalums. There could be all sorts of issues on this drive. I mean, the corrosion on the aluminum here is pretty severe. So this drive may just be dead. And in that case, we can take it apart and look inside. And with that, we're gonna have to end this video here. This is gonna have to be a part 1, and in part 2 is when I actually hook up a test bench to these hard drives and test out to see which ones work and which ones don't. And if any of them don't work, we'll open them up to take a look inside to see if we can maybe identify what might have gone wrong inside the drives. Hopefully you found this video interesting. If you did, appreciate thumbs up, but if you didn't, you know what to do. I'd love to hear your comments down below about what your thoughts are on these ST-506 or MFM hard drives, and especially let me know if it's worth me making a video about RLL controllers in conjunction with these drives, because I've always thought about doing that, but then I wasn't sure if there was really enough videos worth of content there to make an entire video just about them. I'd like to thank my patrons, of course. Their names are scrolling up the side of the screen, one of the sides. They get early access videos, all that good stuff. You can become a patron at the link in the description below. Hit that subscribe button if you haven't already. Like, subscribe, all the usual YouTube stuff. You've all heard it a million times. So that's gonna be it. So stay healthy, stay safe, and I will see you next time.